Um, so when we write Bernoulli's equation, we're going to choose this point and this point inside. And we write px plus density times vx squared plus density timesghx. And for the interior, we write the same thing. So you start just like with energy, don't think about it, just write down the equation. And that's it. For Bernoulli's equation, that's the only terms you have. You don't have to worry too much about it. In this rocket, and as I said, we're taking AI to be here and AX to be here. So in this rocket, there's no change of height. So we can get rid of that. And in fact, we're assuming that the rocket's in space. So this is a vacuum outside. So that goes away. And so what we get is that PI, the pressure inside, is equal to the density over 2 times Vx squared, and move this term over, minus V inside squared. I want you to give this, however, in terms of PI, rho, and Vx. So how do we get Vi to become Vx? Well, we have the continuity equation. And that says the area times the velocity is a constant. It's something known as, they call it R, but it's the volume flow rate. And it's a constant, so AIVI is also equal to the same thing. That's the continuity equation. Any 2 points, A1, V1 is equal to A2, V2. That's because of incompressibility of fluids and blah, blah, blah. So we want to turn this VI into a VX. So VI, if we divide through by AI, is AX over AI VX. One further thing that, no, leave it like that for now. So I have that PI is equal to rho over 2 Vx squared minus AX over AI squared Vx squared. Or better yet, you should probably write this as rho over 2 Vx squared 1 minus AX over AI squared. Okay, and that's the first part. So that's all I want right here is PI is equal to rho over 2 Vx squared times 1 minus AX over AI squared. Now, we want to solve this for F1, or Fi it should be actually. We want the force internal here. And so we're going to note a couple things here. We have P internal is rho over 2 Vx squared times 1 minus AX over AI squared. Pressure is force over area. So this is actually Fi over AI, but I want you to turn AI into AX. And if you go back and look, you're given that AX is 5/12 AI. So from AX is 5/12, it's smaller than the internal area. We can get AI is 12/5 AX. And that means that if we substitute this in, we get Fi over 12/5 AX is equal to rho over 2 Vx squared 1 minus AX over AI squared. And now I want to solve this for F. So Fi is, moving this over, I want to note something. Rho times AX times Vx. So we said back here that the volume flow rate was AX Vx. The mass flow rate you get by multiplying by the density on both sides. Density of mass over volume, so that would cancel the volume. So this becomes the mass flow rate. And if we go back to our rocket equation, we see that R, this big R, is our mass flow rate in that equation. So rho times AX times Vx over 1/2 12/5 times 1 minus, and I'm going to do something really fast here. AX over AI, if you look, dope. What did I just do? AX over AI would be 5/12. So AX over AI is 5/12 squared. This part right here is also times BX. BX and BX. BX squared, rho, and the AX I moved up. 12/5 I moved up. So that leaves me with FI is R. This is rho AX BX times BX times 1/2 times 12/5 times 1 minus 5/12 squared. And this is going to be a little hard. So this is 6/5 outside. If I multiply it through, I get 6/5 times 6/5 times 5/12 times 5/12. These cancel, this becomes 1, this becomes 2, and what I get is 6/5 minus 5/24. If you do this on your calculator, you're going to get 0.99, which is approximately 1. And we're going to assume it's 1, and we are all good. This is what we have. That is.
Slide, please.
What's that?
Do you mind going back a slide really quick so I can see your work?
So here we started off with this. PI became FI over AI, but AI, if I turn it into AX, is related by this. So I can substitute for AI 12/5 AX. If I break this V into rho VX times VX, AX multiplied by AX on both sides, AX rho VX is your R. That's this term. You still have a VX left over, 1/2. The 12/5 comes up, so you're left with this part. But if you do this math, this ends up being approximately 1. And so what we're left with, are you good, Lucas?
Yeah, so then what we're left with is FI equals rho AX VX squared.
Yes. But rho
Okay.
AX VX is the mass flow rate, which we called R when we did the rocket equation. So this becomes RVX, and all this becomes 1. So we're left with that. Remember that this is M, not A, R, VX. So A is R VX over M naught. Where R is not a radius,
Sorry, can you explain really quick how we went from the rho AX VX squared to R VX?
So rho VX VX, let me actually do this. So we had that F1 was, what was it, 12/5 AX is rho VX times VX, and then this stuff was all times 1. I guess I should actually write it, sorry. Over 2 times 1 minus AX over AI squared. And that AX over AI is 5/12. So doing this, if I multiply through by AX on both sides, and multiply through by 12/5 on both sides, this goes away, and I get F1 is rho AX BX. But this is your mass flow rate times BX. So that accounted for that, times 1/2 times 12/5 times 1 minus 5/12 squared. And this whole term is 1. If you do it, it's 0.99. And this term is your R. Does that make sense, Lucas?
Yes, it does.
Okay. So that actually gives you that F, your thrust, is rho AX VX times VX, but because the thrust is actually M naught A, A is equal to R over Vx over M, I'm sorry, R Vx over M naught. And I gave you some numbers to plug in for part 3. So A, if, let me do that on a new slide. A is R Vx over M naught, which is really rho AX Vx Vx over M naught. Rho is 1,500 kilograms per meter cubed. That's rocket fuel's density. AX is 5/12 of AI. AI is given to you as 7854. So 5/12 is 7854. And 78.54 is 32.725 meters squared. Vx I gave you was 1.2, which may seem small, but you're going to see what the thrust actually is. And M naught was, I believe, 2,300,000. Yep. 2,300,000 kilograms. So this is 1500 times 32.725 times 1.2 times 1.2, all divided by 2,300,000. And I get A is 0.0307 meters per second squared, assuming I did that right. Now, what is the thrust? The thrust is the force, which is M naught times A, which is this times 2,300,000. 230,000, which is 70,686 newtons. Let me double check this stuff really fast. R would be 1,500 times 32.725 times 1.2 is 60,000. Yeah, that's about right. So that would be the thrust. Those numbers aren't even close to what they actually do. They actually generate a lot more thrust, but in this kind of ad hoc thrown together example, that's what you get. You get a very low acceleration, and you get thrust of about 70 kilonewtons. The big thing that I wanted you to take away from this is that we use Bernoulli's equation, which says if you have some pipe that changes size so that A1 and A2 are different and A1 is, say, less than A2, all you have to do is find the pressure here and the pressure here, the velocity here, the velocity here. You have P1 is density times velocity squared over 2 plus density times H1. And then you just write P2 rho V2 squared over 2 plus rho G H2. That's all you start with. In our problem, we said that this side was the exterior stuff. There was no pressure because it was vacuum. And there was no height change, so these went away. So basically the first step is just write this. Next step is to get your variables if you have them. The only thing that you need to remember is if this were open to the atmosphere, it's the same thing as atmosphere. 101,000 pascals. The other equation that you had, though, is what's called the continuity equation, which says AV1 is equal to A2V2. This is also the volume flow rate. And if you want the mass flow rate, you just multiply it by your density. You have a homework question that does that, but I really want to make sure you understand this. And the nice thing about this problem is we're taking Bernoulli's equation and using it to get the rocket equation, which we originally got with momentum. So Bernoulli's equation is just energy if you multiplied everything by volume, assuming everything has the same volume, which we do because it's incompressible the way we derived this equation. When you multiply through by volume, all of these terms become energy, because rho times v is mass. So it's just the energy equation with an extra term PV, and then we cancel the volumes. The trick, though, that throws people is the pressures are static pressures, and that's sometimes difficult to figure out what they are. On an exam like the final exam, if you're not sure, you can always ask me if you're supposed to know the pressure, and if it's atmosphere or whatever, I'll tell you. If I don't specifically tell you in the problem. But that's really the only hard thing. It's pretty much just energy. So what's nice too about it is the other thing that we learned in fluids was P1 is equal to, P2 is equal to P1 plus rho G H1 minus H2. That comes straight from this equation if you assume that there's no velocity at 1 or 2. That will allow you to find the pressure change going up or down in water, etc. As long as you make sure that you define the surface to be at 0 and y going positive up and y going negative down, or h going positive up, h going negative down. So Bernoulli's equation's pretty nice. The only other thing we learned in that fluid chapter was Pascal's, which said, Pascal's principle, which said that the pressure in is equal to the pressure out, which means F1 over A1 is equal to F2 over A2 for an enclosed vessel with an incompressible fluid. And that's a pretty cool concept to do, like hydraulic levers and stuff. Anyway, any questions on this before we move on to the actual lecture today? Also keep in mind at 12:40, I'm going to stop. I should be done by then. I'm going to run and pick up my son. I'll be back in 10 minutes. And then I'm going to go through the fluid homework problem by problem and do them for you or do them with you. So I know a lot of you probably haven't touched that yet. And if we have a little bit of extra time, I'll talk about the homework for today's lecture. Otherwise, I'll do that on Wednesday. Okay, just make sure you get it in by midnight tonight. Hopefully that was useful to you. And hopefully you can hang on to that, and it'll help you on the final, if you're not good at Bernoulli's equations yet. Okay, so in our modules on the PowerPoints, today's PowerPoint's chapter 15, part 1. So I need to talk about your book a little bit. Your book does a good job with some things in the chapter, and it does a horrible job with other things in this chapter. Mostly, I feel like this book assumes that you guys wouldn't be able to figure out differential equations or quite understand them. So this chapter deals with something called simple harmonic motion, which you find by a differential equation. They give you the solutions and kind of talk about it a little bit, but I don't know how good they do of a job with that. Simple harmonic motion is pretty easy. We've seen it before. You just don't know you've seen it before. Then they talk about pendulums, including a torsion pendulum, which I'm not going to talk about because it's pretty much write down an equation, and I don't find it that interesting. I think pendulums are. On next week, we're going to go through oscillations, which are harmonic motion, but I'm going to take you through the full derivation of them, including how to do the derivation for what's called damping, which is when you have friction. And I'm going to show you guys some stuff about differential equations that day that you don't need to know, But if you haven't taken differentials yet and you're scared of them, hopefully it's a nice soft introduction to differentials for you. So next week, when we talk about oscillating systems, what we're going to do is we're going to do the math, and then we're going to look at real systems that oscillate in nature and how to do problems involving those. So you have chapter 15 homework already, but that is all just on stuff that we're doing today. You'll have a few more questions on some stuff for next week, but it'll be like 3 or 4 questions on that homework. Nothing too hard. And then next week, we're also going to do a quick in-class lab where we're going to look at the actual oscillating sine wave and interpret it and find all the different values and understand how it works. So when we go through this stuff, some of it, don't try to write down, just try to listen. I'll try to highlight stuff you can write down, but don't try to write all this stuff down. When we get to important stuff, I'll let you know. There's just a lot of background derivation. I just don't want to give you equations. I want to show you where they come from and why they are what they are. So, okay. And why do we care? So, first of all, a lot of times, whether you're a biologist or a chemist or a physicist, you actually look at the simplest model of your system that you can have. The simplest model is usually something called a restoring force, which means that if you nudge your system a little bit one way or another out of equilibrium, it wants to come back to equilibrium. We've already seen this as a spring force, but this is something called a restoring force. The negative sign means it always acts against the motion. So whichever way you push it, it tries to send it back the other way. This is actually a model for real life behavior of electrons in atoms. If you try to jump them on energy levels, it can be electrons in lattices. If you don't know what that means, it's a way to describe solids and molecules where they're bound together, and the electrons actually act like they're on little springs moving back and forth. Some of that we're going to talk about next week, but for now, just know this. And then cell behavior. What I mean by that is, I'm going to probably get this wrong, so biologists, please be kind. But basically, when cells interact with like different proteins and different stuff, a lot of that behavior can be modeled as a simple restoring force, believe it or not. How that stuff works can be modeled by this super simple idea that the force is just some constant times however far you move it away from equilibrium. And that's why we study it. It ends up being a really powerful, simple tool that's easy to understand, and you have a constant there so you can figure out what the constant is. You can then take this up to higher order stuff by making this constant more terms, basically, making the equation a little bit more complicated. We don't need to worry about that right now. So the first quick introduction to a differential equation. If we assume that this is like a block attached to a spring on a frictionless surface. So you have this wall, you have some block, you assume that there's some equilibrium position where x is 0. If you pull it this way, the force tries to pull it back. If you push on it, the force tries to push it the other way back. And there's no friction there. So that's it. The block has some mass, the spring has some k spring constant, and the force is negative kx. However, if we rearrange that by dividing through by m, we get this. And this is actually a differential equation. If you look at it, A is actually the second derivative of the x, the position function. So your function of t is what we call x of t. The acceleration is the second time derivative of that. And so what we're really saying is the second time derivative of the position is equal to a negative sign times some constant times the position function again. And that equation, in order to solve this, there may be a million solutions to this equation. There may only be one, there may be none. But we need to solve it by finding some function that if you take the second derivative, it gives you back the function itself times a negative sign and times a constant. The game in differential equations is finding those solutions. And you have a couple of different solutions. You have like the homogeneous solution, and then you have a particular solution, and you have border conditions and blah, blah, blah. Some of that we'll talk a little bit about, but for now, just know it's kind of like a game. You're asking yourself what function, when you take the second derivative, gives you a constant, a negative sign, and the function itself back. One of the nice things about differential equations, there's two really nice things in physics. One is that if you find the solution by guessing, by doing some complicated math, either way, you can totally guess, and if it's right, it's right. The second nice thing is in physics, biology, chemistry, nature in general, the differential equations aren't too bad. In mathematics, if you're a math major, you can explore differential equations that get really crazy. But we don't really need to do crazy derivatives and crazy differentials in physics because nature pretty much has some order to it. Anyway, so we can guess solutions. And remember, we're trying to, oh my God, we're trying to guess something that the second derivative with respect to t of our function is equal to negative some constant times the function again. So it needs to give us back our function. So let's try it here. Taking the first derivative of this, x naught is a constant, so we get 2t. Taking the second derivative, we get 2x naught. This is not a constant, a negative sign, and the original x naught t squared back. So that function will not work here. Let's do this one. E of t, the derivative with respect to t is just e of t. So we get x naught e to the t, x naught e to the t. The derivative doesn't change. This gave us back our original function, but there's no constant and there's no negative sign. So that one doesn't work. The derivative of sine is negative cosine. So this would be negative x naught cos omega t. The derivative of the inside gives us omega comes out. Remember, we're doing it with respect to t. Take it again and we get negative omega squared x naught sine omega t. The derivative of cosine of omega t is omega sine t. It stays negative because there's no negative sign when you do that. So this gives us negative omega squared times our original function. And we have a winner. This is negative times our constant. Our constant is omega squared. And this is our original function back. This one would give us x naught 1 over t. Another derivative would be negative 1 over t squared. So that doesn't work. And finally, this one would give us negative 2 x naught over t to the third. And so 6 x naught t to the fourth, which is again not our original function. So the one we have that works is using the function x naught sine omega t, where x naught is wherever our initial position is. Okay, so that's our solution. We go with that. Now, I need to stop here for a minute. You'll see in the book, if you read, that they write this as sine of omega t plus something that's often called the phase. or sometimes the phase. We're not going to deal with that today. We'll deal with that next week. All this is an offset, because if we look at sines and cosines. So sine and cosine, I should really actually do this, where this is 0 and this is 0. So cosine of theta, it would start here. I'm sorry, it would start at 1, -1. If theta was 0, it would start here and it would go down and look something like this, one complete wave. Sine of theta, when sine is 0 or theta is 0, starts at 0 and goes like this. And I expect that you guys know this, but that's a complete sine wave, that's a complete cos wave. So if your particle does not start when time is 0 at 0, then, which obviously ours doesn't, because we have to shove it, say, inward. Some say we moved it in by, I don't know, 0.20 meters to begin with. Then this would have to be at something like 0.20 when it starts. That means that we have to offset this with some phase. We'll deal more with that tomorrow, or I mean next week. You'll see it in the book, though, that there's a phase. Just don't worry about it for right now. For right now, we're just going to pretend like it's 0 and this is our function. Now, I want you guys to see something. So here's a block moving, and hopefully you can see this. Here's a block moving up and down. If we trace out how it moves, so imagine there's a line going right through the middle here, we see that we're getting this sine wave that describes its motion up and down. We're turning motion in the y into a sine wave. We're basically turning it into what looks like a rotation. And the reason we can do that is that if you imagine having a disc, right? So imagine you have a disc and you attach a flashlight to it and you have a screen, right? As this thing goes around, this light is going to go up and down. It's not going to go around. It's going to go up and down. It's basically, our sine wave is describing the position of the particle in only the up-down plane in this case. That's all this is doing, is this sine wave is basically describing how our block initially starts here, it goes here and comes back. The sine wave, because it goes between -1 and 1, gives us a way to find the motion by using something called omega, where omega tells you what part of the period it's in. We'll talk about that in a minute. But essentially, what we're doing is we are still only worrying about the x coordinate, but that sine omega t tells you what part or what region it's in as it varies with time. So we said that our constant, negative constant, was negative omega squared. And if we go back and look, we had that a was equal to negative k over m x. So that means that our negative c has to equal negative k over m. And since we know that that's omega squared, which is equal to negative k over m, we get that omega squared is k over m, where k is our spring constant, m is our mass. If we take the square root of both sides, we get this. Okay, that's important. Omega, for a restoring force, is the square root of k over m. But what the heck is omega? So again, if you remember, in uniform circular motion, we said omega was the speed in radians per second of the wheel or the particle as it goes around and around and around. To find out what omega is, if we assume the time it takes to go all the way around once is this period t, and the distance around is 2 pi rads for 1 revolution, then omega is 2 pi over t. Okay, so we now have that omega is square root of k over m, and omega is 2 pi over t, which tells us that t is 2 pi over omega. All right, so that allows us to basically use omega to tell us where we are in this cycle. I just did that, but writing omega as square root of k over m, if you put that in here, square root of k over m, you see it flips up and you got this nice deal. Now, what about the velocity and the energy? We have the period, we have omega. If this is our function, take the first derivative of this function. The derivative of sine of omega t with respect to t is negative cos omega t times omega, which is right here. So now we can find the velocity at any time. We know that omega is square root of k over m. If we know the spring constant k, and we know the mass of the block or thing or whatever, we have omega. X naught was the initial position of the particle, and then sine of omega t gives us basically the time varying portion of the velocity. Why does the velocity vary? Because if you remember when we had the block and it went from there to out here and back, when it got to these x max, negative x max and positive x max, where this is 0, when it got to those points, it had no velocity. The velocity goes 0, max, 0. I should put equals, sorry. So the velocity on the ends is 0, and the velocity in the center is max. And that's because the energy is always kx squared over 2 plus mv squared over 2. And when v is 0, it's all potential. And when x is 0, it's all kinetic. I know you guys remember that, but so the kinetic energy, 1/2 mv squared, is really 1/2 m, plug in this. And I'm sorry, I have a sign there where it should be a cosine. Yeah, I know, Hamid. I just got that too. This should be cos. I think what I did was I copied and pasted it and I forgot. It's right here. It's wrong there. It should be a cos. And this one should actually have a negative sign there, but it doesn't matter because it's going to, oh no, it doesn't have a negative. I'm sorry, I'm thinking of the acceleration.
Excuse me. Also, the derivative of sine is cosine. So where does that negative come from?
Oh, the derivative of sine is negative cosine. The derivative of cosine is sine.
No, the derivative of sine is cosine, and the derivative of cosine is negative sine.
Hang on and listen. You're wrong. So draw it, Hamid. Sine goes like this, right?
Yes.
And cosine goes like this. Okay. Cosine is decreasing, right?
Yes.
At the beginning. So sine, though, the slope of sine is decreasing.
No, I'm sure that the
hang on, stop. Hamid, stop. I'll just solve it for you this way.
Are you thinking of the integral, Hamid?
Yeah, I think.
No, the derivative of sine is cosine. Yeah, look at the first one. Sine is cosine, and the cosine is negative sine.
Yes.
Yeah.
That's what I said, Hamid. Where am I?
Oh, Professor, you have negative cosine.
Yeah, this is not negative cosine. This is positive cosine.
Yeah.
That's what I'm saying.
Why is there?
No. Dude,
Because the derivative of sine is cosine.
okay, so, yeah, I might have got this screwed up. I told you I've been foggy. So, derivative of sine should be sine of omega t. Stop everybody for a second.
Everyone stop.
Yeah, everyone stop. So the derivative of sine is, did I screw that up? Let me get this straight in my head, because and I'll explain something in a second, but that's not what I want. Why can't I define this?
It's always the basic stuff where we
Derivative of sine and
mess
cosine,
up.
derivative of cos is negative sine.
Right.
So does that mess
Yeah.
us up for a second? This is cos omega t. No, that still doesn't mess us up. One of the things I hate about this, and the reason why, so this is fine. If you go back in there, and I'm sorry, you guys, for that mess up. If we go back to here, this holds true, that negative sign is still there. I'm going to tell you.
Oh yeah, because it's a second derivative. Okay, yeah.
Yeah, that negative sign is still there.
Mhm.
This negative sign is not here,
And here, the second.
but
Yeah.
the problem here is actually the way your book does this. So I don't like the way they do their, the way they just choose sign. You'll see next week, but really what you should do for this derivative, or I mean, for this differential equation, is you should say it's cosine of omega t and sine of omega t, x naught and x naught. That it's a combination of these two. It's not just sine, it's actually a combination. And then you kill off one of them with your boundary condition. Your boundary condition is that x naught is equal to, say, like 0.1 or whatever. If t is equal to 0, x naught is equal to 0.1, that can't be true. So it has to be cosine. I don't know why your book chooses sine. I'm used to cosine, which goes negative and then goes negative, which is, I think, what I had in my head, which is why it's easy to forget. And while I hate messing up, at least it's somewhat informative that I did mess up. So yes, Hamid's right. Sorry, Hamid, for sticking to my guns on that and being totally wrong.
Thank you. Thank you.
We're all human.
Which always happens. Every time you stick to your guns and you tell people they're wrong, it's usually you that's wrong. So yeah, I'm sorry, you guys. Signs always mess up. But anyway, so from here on out, hopefully we'll be okay. So this is true. And if you plug in the X to the potential energy and you plug in B to the kinetic energy, you get this. And remember, our energy is going to be kinetic energy plus potential energy, right? So it's these two things added together. When we do that, and again, this doesn't need to be there, what you see is, number one, remember that m times omega, this is all squared. So this is squared, squared, and squared. And this is squared, squared. Remember that m times omega squared, m omega squared, here would be m times k over m, which is just k. So this term just becomes k x naught squared cos squared. This becomes k x naught squared sine squared. That is equal to 1. And you get that the total energy at any time is simply equal to your spring constant times your initial position squared times half. But knowing these two, knowing that the kinetic energy is 1/2 m omega squared. Am I doing that wrong? Yeah, m omega squared x naught squared cos squared omega t, and the potential energy at any time is 1/2 k x naught squared sine squared, sine squared omega t. You can just plug in t and find what the kinetic energy or the potential energy it is at any time. Going back to here, and I'm gonna
Professor,
a little bit, yeah.
how did you get the position function?
We guessed.
Oh, okay, cool.
We guessed that it had to be sine or cosine or e to the x, because those are the only functions that they alternate with the derivative.
Right.
If you take the second derivative, you get the function back, I should say. E to the x always gives you the function back. Cos and sine give you the function back on the second derivative. But we chose sine because your book did.
Oh, okay. Why is the omega inside?
Actually, when I say that it's this, with this phase angle, it actually turns out that that could be cosine if you add 90 degrees and blah, 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 blah. So
Is
it's,
that an?
this is just like a little delta. Some people
Oh,
use
okay.
a little delta for the phase. It's just an additional angle.
Yeah.
Because you're not starting at 0. In fact, you can't start at 0 with this, because that would mean that at time 0, you're at 0, which
Yeah.
wouldn't make a whole lot of sense. I mean, I guess it could if you knew what the velocity was at that point, but it doesn't really make.
And then it's omega times t because that will give us like the distance in radians,
Omega
right?
times t is radians per second times second, so it will give you radians.
Radians. Okay, got it. Makes sense.
It basically, essentially what we're doing is the sine part of this is simply alternating between -1 and 1. And
Yeah.
our system is alternating between negative x max and x max. So sine is like the temporal factor that's just telling you where it is at any time. And by taking the derivative of this once, you get the velocity. Taking the derivative again, you get the acceleration, which is what we did originally. We just assumed that it was x, right? We said, oh, x, and the derivative of x with time is the velocity, and the derivative of the velocity with time is the acceleration, or the derivative of x squared is the acceleration. So if you took one more derivative of this, you would get the acceleration. So after all that, and my stupid negative sign, let's do a quick problem here. So if we had a mass of 2 kilograms and it was initially at 0.22, so it's away from equilibrium, it was pulled that way. M is 2, K is 450, X naught is 0.22. What is omega? We know omega is square root of K over M. So this is 450 divided by 2, which is 225, which is 25, right? 25 times 25. Square root of 225. Oh, sorry, 15. Can't do math today. Omega is 15 rad per second. So we already know now that our function with respect to t is going to be x naught sine omega t. And this would be 0.22, which is our x naught, sine of 15t. In radians, that argument needs to be in radians. What is our period? Our period is 2 pi over omega, which is 2 pi over 15. 2 times pi divided by 15 is 4.42 seconds. That is the time it takes to go from the initial position to the negative of the initial position and back. So it's going to go one complete cycle in a period of 0.42 seconds, 0.4188 actually. Now, what is the total energy at any time? The energy is k to the half x naught squared at any time, the total, kinetic plus potential. This would be 450 over 2 times 0.22 squared. So that would be 225 times 0.22 times 0.22 is about 10.9 joules. And what is V at 1.3? What is X at 1.3? So we know that X is X naught sine omega t. X naught is 0.22. Sine omega is 15 times 1.3 seconds. X is 0.133 if you want it, meters. So it's at about 13.3 centimeters. V of t is the derivative of x. So that is omega x naught cos omega t, which is equal to 15 times 0.22 times cosine of 15 times 1.3, which is 2.63 meters per second. And that's it. That's about as hard as this gets. There are a couple of other little harder things that we can do. There's a really good problem I want you to look up. Sorry. I want you to look up in the book that shows you something kind of cool, but we'll talk about that next week. Essentially, though, if you were given X and V and A at some time, what could you find? So let's look at these. So we said that X was X naught cos, I'm sorry, sine omega t. V was X naught omega cos omega t. And A was negative X naught omega squared sine omega t. So what we can do is, what if we went X over A? What would we get? We would get X naught sine omega t over negative X naught omega squared sine omega t, which means X over A is negative 1 over omega squared. So if you were given these two, you could use them to find omega. If you knew these at the same time, you could find omega. And what if we did X over B? We will get X naught sine over X naught omega cos, which gives us tan of omega t over omega. So I should put omega t's here. But... So you could actually, if you knew t, or if you knew omega, I mean, you could find out what t was, even if you didn't know what t was. There's other ways to find other things on here, but essentially you could use this to then use this to find t, or I'm sorry, use this to find omega, use this to find t, and then plug t back in to find x naught. There's a problem that they do that in your book. So hold on, let me go grab the number of that problem. Oh. So the number of that problem is 1501, 1502, 1502. Yeah, and for whatever reason, they're using cosine, which is where the negative sign comes from, and blah, 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 in that problem, but whatever. Should book do that? Is that what I got myself messed up on? Yep. Okay. So why I'm messed up in my head is your book always chooses cosine, which does make more sense because this thing should have a phase if it's sine. So let's talk about phase, and we'll talk about this right now. Blah, 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 blah. Okay, so imagine that we have a block here, and it's at some, I don't know, shouldn't put that, I should put 0. It's at x naught is negative 0.3, okay? And we know that K and M, K is 100 meters, M is 10 kilograms. Therefore, omega is square root of K over M, which would be square root of 10. 3.16. I'll leave it at that. Now, what we really should write is that our x of t is x naught cosine of omega t plus some phase. You can either write this or that for the phase. So we know at t is equal to 0, x naught is negative 0.3, okay? When t is equal to 0, the initial condition. So that means that 0.3 negative 0.3 cos, this is 0 of phi, right? Yeah, so if I divide through and flip sides, this is cos of phi is negative 0.3 divided by a negative 0.3, which is obviously 1, right? So cosine of phi equaling 1 means phi is arc cosine of 1, which is 0, okay? So that tells us that phi is 0 in this case, which is why your book is using the function x of t is cosine omega t x naught. When they do that, v of t is the derivative of this, and you would get negative omega x naught sine, and I'm still foggy, you guys, which is why I flipped all my signs back there. Cosines and sines and sines. A of t is negative omega squared x naught cos omega t. So for a block, if you start at x max, the initial x naught is your x max. But what if you don't start there? Okay. So what if we're not starting there? What if instead we know that x max is 0.4, say, but our initial x position, x when t is equal to 0, is only 0.2. And again, we know that omega is whatever we said, square root of 10. We're going to need that. Well, we don't need that actually. So we're saying when time is 0, plugging stuff in, 0.2 is equal to 0.4 cos omega t plus phi, but this is 0 because t is 0. So cos of phi is 0.2 divided by 0.4, which is a half. That means phi is arc cosine of 1/2. Now, you need to be in radians. Everything should be in radians. So arc cosine of 0.5 is about 1.047 radians. Okay, that means your phase now is x of t is x naught, which we said was 0.4, cos omega, which we said was square root of 10 times t, plus our phase. Actually, let me write it this way first. X naught cos omega t plus the plus 1.047. Now, let's double check that. 0.4 times cosine of 1.047 gives us 0.2. And from there on, all of these, why did you do that? From there on, all of these should actually have this phase because it's actually there. I didn't want to talk about this so much today. We'll talk about it more next time. But because I managed to flip this to a sine, the nice thing is that it really doesn't matter whether you choose sine or cosine. If this were sine of omega t plus, well, let me do it on the next page. If I did this as sine of omega t plus the phase, and again, I chose, so again, I chose x when t was 0 to be 0.2, and I chose x naught to be 0.4. I could say this was 0.2, 0.4, sine of 0 plus phase. Now I get sine of my phase, and I should actually stop flipping them. Sine of my phase is 0.2 over 0.4, which is 0.5. The angle is arc sine of 1/2, which is arc sine of 0.5, which is 0.524. And now my x would be x naught sine of omega t plus phi, which is 0.4 sine of omega t. Well, I guess I can put in square root of 10 times t plus 0.524. Let's double check it. If we plug in t is 0, 0.4 times sine of 0.524 is 0.2. So it doesn't matter whether you choose sine or cosine to be the function. Turns out they both work. They just have different phases of where they start. That's a little weird, right? But that's because if you look at the graph of sine and cosine, and maybe this will help you understand phases. So if I start, sine starts here, comes up, goes down, comes back. Cosine starts here, goes down, comes back up, and ends back here, okay? So this is the halfway point, this is the halfway point. Really, what it is, if I continue this up, right, you can see that this is a cosine. So what it really is that sine is just a cosine offset by 90 degrees, or cosine is a sine offset by 90 degrees, whichever way you want to see it. They're exactly the same function, they just have a slightly different phase to them. So if I add sine of the angle plus pi half radians, I get cosine of the angle, right? That's what's going on here. You can choose either one. The book chooses cosine because they're assuming that the phase angle is 0, And that way at time t, they get cosine of 0, which gives them the maximum. But that's not always true. What if you were measuring at different times? You started measuring at time at 0. So if, I guess I'll say this, if at maximum when t equals 0, x naught cos omega t. If not at max, otherwise known as x naught, then it's x naught cos omega t plus some b. Anyway, we're going to go over this a lot more in next week when we talk about oscillations, and I'll cover this. And hopefully I won't screw up my signs again. So let me talk about pendulums for a quick half hour. This won't take too long and we'll learn some cool stuff about pendulums. And yeah. So a simple pendulum versus a physical pendulum. I mentioned when we did our pendulum lab last week that a lot of you might have already learned this in physics somewhere, but I want you to forget that equation. That equation that says, oh, for a pendulum, the period is 2 pi L over G. A simple pendulum is just a string tied to an axis point with a mass on the end. And you assume that there's no mass to the string. A physical pendulum is any other object that you hook to some axis. It could be a rod. It could be a string that actually has mass. It could be a sphere on the end. They're going to go back and forth, and that's one period, right? 0, the initial angle. It's going to go back and forth, and that's one period. But I want to derive for you any pendulum using what we've already learned today. So for any pendulum, let's start by doing the torque diagram. And the torque diagram, if we have just a point mass at some angle. At the center of that point mass, there's a force of gravity or a weight down mg. This happens to be L, but it's also our R vector for the force, right? The R vector out to the force. This is the same angle. The torque associated with that, then, if I draw a torque diagram, I'm going to assume that alpha rotates the normal counterclockwise way positive. All I have to do is draw R and draw F, which is mg, and I see that this is a negative torque. So torque is I alpha. I alpha is, I wrote little r here, so let's actually change that back to little r. So you have a torque, and it's R cross F, sine of the angle between them. So this is the angle between, why do you do that to me every time? This is the angle between R and F, or R and mg. And that is our equation here. Now, we get alpha is negative R mg over whatever the moment of inertia is. We'll talk about this in a minute, times sine of theta. Now, remember we also talked last week about the small angle approximation, and for small angles, sine of theta is essentially theta. So we can change our sine of theta to theta and we get this. And do you recognize this? We had A was negative omega squared over or times x, A of t, x of t. So from this, we can see that r omega squared is mgr over I. And recalling that 2 pi over omega was our period, omega is obviously mgr over I with a square root. doing exactly what we did at the beginning to get omega was k over m. It's that. Because when we're talking about radial acceleration, the x value is theta, right? So we get this, and then plugging that into the period equation, we get this, okay? So we had that omega is mgr over I, and since it's in the bottom, it gets flipped, we get this. Now, I is the moment of inertia for whatever you made your pendulum out of. R is the distance to the center of mass of that moment of inertia. So let's do a couple of soft examples to prove that's true. So simple pendulum. The mass is at a distance L, mg. The center of mass of the point mass is at L, right? So little r is L. And what we get is the period is 2 pi I over mgr. I for a point mass is just mr squared, but in this case our r is L, so it's ml squared. So we get 2 pi ml squared over mg, little r is again L, canceling one L, canceling the m's, and you get that the period is 2 pi L over g. Now this is important though. I want you to remember this, not this. Commit this to memory. I in that is the moment of inertia of the whole thing. So if you have like two rods stuck together and you had to for some reason total them up, and we're going to do that in a minute with a different thing, you have to find I. R is the distance to the center of mass of whatever you're using as the pendulum. The center of mass of a point mass is located all the way to L. Now for a rod, about one end, right? What is the moment of inertia about a rod? And R is going to be L to the half. The moment of inertia for a rod about one end is ml squared over 3. Okay, so we have R is L to the half, the distance from the axis to the center of mass, and the moment of inertia about this axis is ml squared over 3. So plugging that in, omega is mgr over I, which is mgl to the half over ml squared over 3. M's cancel, the 3 goes up, the 2 comes down, you end up with 3g over 2l. But remember that omega is flipped, so this becomes 2l over 3g. Now, here's a quick conceptual question for you. We have for a simple pendulum, 2 pi L over G. For a physical pendulum made of a rod, that number in the square root is root 2 over 3. That means that the rod actually has a faster period. Yeah, I will in a second, Sammy. The rod has a faster period than the rod has a faster period because the rod's period, so simple pendulum, is 2 pi L over G. The rod is 2 pi times 2/3 L over G. So this is going to be faster than the simple pendulum. Why? Well, the reason is for the rod, more of the mass is closer to the axis of rotation, right? Because the center of gravity is closer. the center of gravity for a simple pendulum is the point mass all the way at L. For the rod, most of the mass is here. Obviously, you can't really compare them because you would have to know their lengths and blah, 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 but that's why. So how about for a hollow sphere? So you might say, for a hollow sphere, I'm just going to treat it like a simple pendulum, and this distance is L. But you can't, because about an axis through its center, a hollow sphere has I of 3/5 m r squared. But it's not rotating about its center. It's rotating about this axis. So you have to use the parallel axis theorem that we learned, which says ICOM plus MD squared. D in this case, we're moving it from the center to the axis point, L. So IP parallel becomes 3/5 m r squared, where r is the radius of the hollow sphere, plus m L squared. So now let's plug that into, again, our equation is T is 2 pi I over mgr. R in this case is again L, this R is. So this becomes 2 pi 3/5 mr squared plus ml squared over mgl, which looks kind of bad. Kind of annoying to have to figure out. However, if R is significantly smaller than L, you just ignore it and you get ml squared over mlg, which means that it becomes a simple pendulum as long as R is very, very small compared to the length of your string. If you have it on a string 100 centimeters long and the radius of your hollow sphere is like a millimeter, then essentially it is a simple pendulum. So there's two ways to see that, and that's that either a simple pendulum is the limiting case for a very long string with a very small radius, or yeah, I guess that's the only way to say it. But anyway, yeah. So that's not too bad. You could, even if you were given the radius and L, you could just plug them in and get that number. It's not too hard. But the key takeaway here is that for a hollow sphere, you have to use the parallel axis theorem to get the correct moment of inertia for the pendulum. All right, so let's actually use these equations to do something. Say you climb to the top of, I don't know, Mount Everest, and you pull out a pendulum that has a length of 30 centimeters, 0.3 meters. And you note that it's got a period of 1.4 seconds, goes back and forth every 1.4 seconds. You could find G atop that mountain using just this simple pendulum equation. So first of all, square this, square both sides. You get T squared is 4 pi squared L over G. Solve for G, multiply by G, divide by T squared. And you get G is 4 pi squared L over T squared. Plugging these in with L is 0.3 and T is 1.4, I get 4 times pi times 0.3 divided by 1.4 times 1.4. I get 6.043 meters per second squared. We talked about this when we did our pendulum lab, but that's kind of beautiful. All you would need is a string and a rock and a somewhat reliable way of determining what your time is, how long it takes to go back and forth. But hey, who hasn't counted seconds by Mississippi, right? One Mississippi, or you probably have some other way that you count a second. I always do Mississippi's. So I could get just a long enough string, you know, maybe. Anyway, I could find the gravitational constant, assuming I have a good, reliable clock and I know the distance of my pendulum. That's kind of cool. So, second type of problem is, what about if we're on the moon? So we saw that a 1 meter long simple pendulum has a period of 2 seconds on the Earth's surface. If the moon's gravity is a sixth that of Earth, what would the period be on the moon? All you have to do is exchange. G is now 1/6 G. Okay, so we would go 2 pi times L over 1/6 G, which is 2 pi times 6 L over G. In fact, you could actually say that 2 pi L over G was 2 seconds. And since this is that multiplied by square root of 6 times 2 pi L over G, then 2 times square root of 6 is 4.9 seconds. You could do it either way. You could just solve this right here if you wanted, with 6 times L is 1 meter, G is 9.8. Or you could recognize that it's simply square root of 6 times that, either way. So on the moon, a pendulum would have a period more than twice as long, almost 2.5 times as long as on Earth, because of the gravity. I want you guys to think about that a bit. Gravity is what makes the pendulum go back and forth forever. And assuming that there's no other forces on it, like air resistance or tensions or friction up in the axis point in the string and blah, blah, blah. The only thing that matters is the length and the gravitational constant. That's kind of cool that works. Hopefully, maybe one of you will get to go to the moon and try it and tell me if it works someday. Since they'll maybe be sending people soon by the time you guys are, 30. All right, so the last fun one I want to do before we got to take our 10-minute break. And this actually surprised me because this problem is in university physics. It's a cool problem using pendulums. But there was a group at some college that did research and figured out the walking speed of a T-Rex. And they got basically, this was only like 2 weeks ago, they got basically the same answer that has been in university physics forever. So imagine that you have a T-Rex has a leg of length 3.1 meters. And you're looking at its footsteps, so its right foot and its left foot. And you realize that these steps are occurring every 4 meters, right? So you're going to assume that what this is it's a physical pendulum, 3.1 meters in length, and that every time it hits, it, basically is one full period. So one period is going to be that. And you want to determine what its speed was when it was walking from that. So the distance was 4 meters, but you need to find the time. Assuming this is a physical pendulum of a rod about one end with I equal to ml squared over 3, we're going to solve this thing. Now, to the center of mass of this, we're going to assume R is L to the half. So period is 2 pi I over mgr, which, no surprise, is 2/3 L over G. This is L to the half, and this is ml squared over 3, so you get everything canceling. We already did that though. So what is our period here? 2 pi times pi times square root of 2 times the length is 2 times 3.1, 6.2, divided by 3 times g, 1.8, and I get 2.89, let's call it, 9 seconds. So V would be 4 divided by 2.89. 1.39, 1.39 meters per second. V is equal to 1.39 meters per second. Essentially, you multiply that by 2.1 and you get the miles per hour. So times 2.1 is about 2.9 miles per hour. How fast do you walk, Lucas? Do you know? Average human walks about 3 miles per hour, unless you're really tall. So a Tyrannosaurus Rex walked at about the same pace as a human. This is the same math, just cleaner. You end up getting, how did my time get so off? Oh no, my time was right. You end up getting about 3.1 miles per hour, I think is what the book said. I always use a rule of thumb of about 2.1 miles per hour. Or multiplying meters per second by 2.1 will give you miles per hour. But yeah, so using a physical pendulum will give you the walking speed of a T-Rex. And then there were these people at some university that did a big study on the bones and the footsteps and figured out that that's about how fast they walk, which is kind of cool that it gives an answer that's close to what paleontologists believe is true, or biologists, or whatever they are. One other story that's been in the news that you guys should keep an eye on, since we just did the energy and orbits, China launched a really big rocket to put, I guess they're building their own space station, and I'm not bashing China here, but they launched a rocket up there and it was supposed to have a controlled fall back to Earth. That thing is now tumbling and they're not sure when it's going to hit the ground. Since most of the Earth is water, they're hoping that it'll hit in the water. But they're not sure where it's going to land. Way back, I don't even know if I was born yet, Space Lab fell out of the sky. Space Lab was like a precursor to the space station, and it landed in Australia. Essentially, what Russia and China used to do, and I'm sure we probably did too, is when they had something up there, a satellite that they didn't want anyone to get, they would blow it up. They had explosives on them that would blow them up so that no one could get the technology if something went wrong. And I think we got mad about that because all the junk that's floating up there, because as you learned as you learned in chapter 13, once you put it up there, it just stays up there. You've actually got to take it out of orbit. I don't know if that's obvious to you, but from the energy equation for gravity, you have to actually give it some energy to stop it so that it will fall back to Earth. In the case of the rocket, it's tumbling, so it's losing energy. It's actually something worth noting. People talk about shooting garbage into the sun. It's actually harder to shoot something into the sun than it is to shoot it out of our atmosphere or out of our solar system. So we'd be better off just shooting it off into space. All you have to do is hit the escape speed of the Earth. To get it to the sun, you have to slow it down enough for it to fall in to the sun without falling into a stable orbit. And that actually takes a lot of energy, which is weird. You would think that it would be easier to launch something into the sun than to launch it out of our solar system, but it's not. So yeah, keep an eye on that. Again, we're going to go over oscillations again next week. And I'll show you about choosing the right function. We're actually going to do it the right way by choosing sine and cosine and eliminating them using initial conditions, which will get rid of the sine term. I know it doesn't matter if it's sine or cosine, so when I wrote this, I wrote sine and I should have paid more attention. If you need it for your homework, make sure you use cosine. So make sure that you do this, since I have 5 more minutes before I got to take a break and go get my son. So make sure you use this instead of my stupid notes. So mad at myself. X naught cos omega t. Omega is square root of k over m. T is 2 pi over omega, if you need it. Therefore, V of t is negative x naught omega sine omega t, and A of t is negative x naught omega squared cos omega t. So other than that, I'll see you guys in 10 minutes. I'm going to stop. I'm just going to pause my screen and I'll be back in 10 minutes. All right, I'm back. So what I want to do now is actually go over the homework is actually available, Hajar. But it's not actually on the PowerPoint. What I'm going to do on here, yeah. Sorry, I gotta calm down for a second. Stop trying to do 10 million things. So the new homework, I'll go over really briefly just what the problems are, and then I'm going to go over the homework for chapter 14, and I'll actually break down how to do it and do numbers and all that good stuff. So homework 14 covers topics that we just talked about. Question 1 says an object undergoing simple harmonic motion takes 0.42 seconds to travel from 0 velocity to 0 velocity. And the distance between those points is 49 centimeters. So they want you to calculate the period. The period, though, remember, is 1 point back. So it goes to 0, comes back to 0. So it would have to be double that. The frequency, if you know the period, you can get omega. I'm sorry. The frequency is 1 over the period. I should have mentioned that. I didn't, but I think I did at some point in the semester. The period is the number of seconds it takes to do 1 cycle. The frequency is the number of cycles in 1 second. But what that means is that t is the inverse of the frequency, and the frequency is the inverse of t. Frequency is written in hertz, which is 1 per second. We've kind of gone over that in lab. So here they just, once you know that, you can get that. And then the amplitude is how far from the 0 point it travels. And we'll talk more about that next week. But the amplitude would be half of this 49 centimeters. This is another one. The amplitude is that x naught. The reason why we say that is if we have our cosine function and it starts at x naught, and this is 0 and this is negative x naught, and it's a cosine function and it goes like that and comes back up, right? So if it starts here, when they say amplitude, they mean x naught. It's whatever the x max is, and we're going to go over that more next week. But for now, that amplitude, just read that as x naught, and it gives you the period. So they want to know the magnitude of the force. meaning they want MA. They gave you M. You should be able to find A if you know X naught and the period. Period will let you get omega, and you should know what those things. If the oscillations are preceded by a spring, what is the spring constant? Remember, omega is square root of K over M. We can talk more about that. This is an oscillation question, but what you need to do is find the max blade speed, the magnitude of the max blade acceleration. That happens when cosine or sine are 1. I'll give you that hint, but we'll talk more about that next week. But that's in your book. Oscillating spring takes 0.54 seconds to begin repeating its motion. That means that this is the period. They want the frequency. They want the angular frequency. That shouldn't be too hard. Mechanical energy, if it has a spring constant K and an amplitude X naught of 1.5. If it's not clear, they want the total energy. So 1/2 K X naught. This is a little bit harder. When the displacement is 1/4 X naught. So they says XM there, they mean X naught. That means that when X is equal to 1/4 X naught, what fraction of the energy is kinetic potential at what displacement? In terms of amplitude is the energy, half kinetic, half potential. So remember that your energy total is K X naught or X max squared over 2, but that's equal to the kinetic energy plus the potential energy. So when they ask here, when the amplitude is 1/4 of X max, what fraction is kinetic, what is potential? What they're asking you to do is find kinetic energy over total when, what was it? 1/4. When X equals 1/4 X naught or X max, whichever way you want to say. And then potential energy over total. The kinetic energy was mv squared over 2, which is, and the kinetic energy is, so, sorry, my brain just went away for a second. Potential energy is kx squared over 2. If I plug in for V, negative omega x naught sine omega t, and I plug in for x naught cos omega t, when x is equal to 1/4 x naught, so let me do this over here. So x of t is equal to x naught cos omega t. So when this is 1/4 x naught cos omega t, what they're saying is, what do they give us? We can find what omega t is from this. So divide through by x naught and you get that cos omega t is 1/4. Omega t is arc cos of 1/4, which if I do that with my calculator, remember in radians, I get 1.318. And then once I have that, I can find this because this one would just be negative omega x naught sine omega t all squared. And this one would be k over 2 x naught cos omega t squared, everything in there squared. And when you do that, you're going to need the omega t, because if we put either one of those over total, so for this one, we would get m times negative omega x naught sine omega t, assume we know omega t squared, over to the half, over k x naught squared over 2, which would be equal to the halves would cancel, the x naughts would cancel. This would be omega squared sine squared omega t, everything in the parentheses. But m over k is also omega squared. So this is omega to the fourth sine squared omega t. Right? That is kinetic energy over total energy. And then for potential energy over total, you would have k x naught squared cos squared omega t over 2 divided by k x naught squared over 2. So you would just get cos squared omega t would be that ratio. Got to find omega t though, using that first bit of information as we did right here. Okay. It's a bit of a pain, but, and then it wants to find the displacement in terms of amplitude. Is the energy of the system half kinetic and half potential? So that means that you want to know what x is when the potential energy is equal to half the total energy. So the potential energy is k x naught squared cos squared omega t over 2. And this would be 1/2 times k x naught squared over 2. So the k's cancel, the x naught cancel, and we get cos squared omega t is equal to 1/2. So omega t, if I take the square root, omega t is, well, let me do it this way, 1 over root 2. So cos of 1 over root 2 omega t is equal to that. You can get omega t, and then x is equal to x naught cos omega t. So you could actually just plug that in and you would see that this is 1 over root 2. So x should be equal to x naught divided by root 2. I realized I didn't need to actually do that one. I don't know why that's slightly off. Or am I just being foggy still? Yeah, that's right. Sorry, that is 1 over root 2. Okay, so onward. Here's a pendulum problem. So treat this as it's a simple pendulum. You know the period, and if she stands up, she raises it by 33.3. So remember, for a simple pendulum, t is going to be 2 pi L over G. And they gave you what this was. And then we're going to make L be minus 33.3 centimeters. Okay, so let's find L here. L would equal t squared is 4 pi squared L over G. So L would equal G times t squared over 4 pi squared. And you can find L. And then subtract that, but L will be in meters, so subtract 0.333. So let's do that really fast. 9.8, they gave me a period of 8.53 seconds. So 9.8 times 8.53 times 8.53 divided by 4 times pi. I get 18.06 meters, 18.062 minus 0.333. I get the new length is, so length new is 17.729 meters. And my period would now be 2 pi L over G. So divide that by 9.8, take the square root of that answer, times 2 times pi, and I get 8.45, which isn't much of a change, but it's correct. Okay. So this time you're treating it as a simple pendulum. Find the length using 8.53 seconds as the period. Once you do that, plug the new length in by taking the length minus. It's minus because she stood up, so she got closer to the axis of rotation, which means L had to decrease by, for me, 33.3 centimeters. But remember to put it in newtons or meters. For number 8, I don't know why my being so weird. For number 8, here you're just going to have 2 rods attached there, and the bottom rod is going to act like a pendulum. This is exactly like the T-Rex or just a rod about 1 n, which if you remember was 2 pi times square root of 2L over 3G. So 2 times pi times square root of 2 times the length is 4, divided by 3 times 9.8. And I get slightly different. Why am I getting slightly different? Am I choosing the wrong A? Oh, maybe they're supposed to be joined together? Oh, I'm such a moron. Okay, I get what's going on here. I was assuming the gray stick wouldn't rotate. The gray stick will also rotate. Therefore, let's go back to here and do this, because this is actually good. Remember I told you to memorize it this way, I over mgr. Now, R is going to go to the center of mass of these guys, okay? And the center of mass of this is going to be somewhere along here, but you're going to have to figure it out in the X. They're assuming why are they assuming it's L to the 4th? I guess they just decided it by doing the center of mass, which we can do. So center of mass on this one, if this is 4 meters and this is that, and they're both, we don't know what the mass is. But we know that they're both the same. So you would have M, it would be along the center, but in the Y direction, you would have M and this one at Y is equal to 0. So hold on. Big M times Y to the center of mass, where big M is 2M, is equal to, let's call this M1 and M2. This is Y is equal to 0, and this is Y is equal to, I'm going to put it upside down. Y is equal to 0, and then this would be Y is equal to 2 meters. That's where the center of mass of this guy is, and we have to add them. So M times 0 plus M times 2. That doesn't give me 4. That in fact gives me that in fact gives me just 1. What am I not seeing here? Let me go back and look at it. I'm not seeing something. Oh, I'm totally dumb. So yes, it is 1 meter. But that means, I'm telling you guys, I'm foggy. So I don't expect you to remember this, but when we computed the center of mass, this was the total mass. Y of the center of mass is equal to m1 y1 plus m2 y2. If I set this up so that the gray one is at y is equal to 0, so that's m1 and y1. And then this one, since it's 4 long and I know it's at the center, m2 is, y2 is at 2 meters. So I get 2 times m, y center of mass is equal to m1 times 0 plus m2, which is little m times 2. Y center of mass is 2m over 2m, which is 1 meter. And this becomes the center of mass of the entire thing. But now I need to flip it. So since this thing's at L, it should actually be at 3/4 L. I don't know why they have 1/4 there. If you're counting from the bottom, hang on a sec. Inside. No, come on. So, okay. And then, so our R is to our center of mass. So our little r should be, oh, sorry, it's actually 1/4. 1/4 L. So we're going from here back, and that's only 1/4 of L, which is what they had. I is the moment of inertia of the first rod about one end plus the moment of inertia of the second rod about its center. 4 over 4 is 4/12, so this is 5/12 ml squared, and R is 1/4. So our period is T is 2 pi I over mg little r, which is 2 pi 5/12 ml squared over mg L to the 4th. That becomes m cancel, 1 L cancels, and I get 4 over 12 is 1/3, so I get 5/3 L over G, which is, L is 4 meters. 2 times pi times square root of 5 times 4 meters, which is 20, divided by 3 times 9.8. And that's 5.18. 5.18 seconds. What did I mess up there? Oh, I'm still dumb. I forgot this M is actually 2M because there's 2 of them. So total M. So this is 2M, which ends up being 6. This M is 2M because it's both of them, the weight of both of them at the center of mass. So that ends up being 2 times pi times square root of 5 times L is 20 divided by 6 times 9.8. And that is 3.66 like it should be. Sorry about that. Yep, that one's weird. Just don't forget, period is 2 pi I over mg little r. Finding the center of mass, you get L to the 4th because it's right here. The m in mgr is 2m. I is ml to the 12, ml squared to the 12th, ml squared to the 3rd. This one's going about its center, this one's going about its one end. Final one of these. Uniform meter stick with a pivot point which is at a distance x is from the end of the stick. What is the period of oscillation? So let's do this. All right, so remember, our period is 2 pi L I over G, I over mgr. And this thing is supposed to be a meter stick with a pivot point that is a distance of 20.3 centimeters from the end of the stick. So this thing's trying to rotate at a point here where this is 0.203 meters. Okay, so we need to find I. We know that I, center of mass of a rod, is ml squared over 12, and we're moving, this whole thing is 1 meter long. So we're moving, this half is 5, 0.5 meters minus 0.203 meters is our D. That's how far we're moving from the center axis. That is obviously 29.297. So I parallel is ml squared over 12 plus md squared, which is ml squared over 12 plus d is 0.297. M times 0.297 squared. Okay. And R, if we're here to the center of mass, is also 0.297. The center of mass of this rod is at the center here, which is 0.297 away from the axis of rotation. So this is 2 pi times ml squared over 12 plus m times 0.297 squared over mg 0.297. The m's all cancel. What was our L? Our L was a meter. Duh. So our L is 1, so this becomes 2 pi times 1/12 plus 0.297 squared over g times 0.297. Let's make sure we're right. So 1/12 plus 0.297 times 0.297. Divide that whole thing by 9.8 times 0.297. And I get 0.0588. Take the square root of that answer, multiply by 2 and by pi, and I get 1.52 seconds. 1.5366. Okay, so key takeaway here. Pendulums, 2 pi square root of I over mgr. I is the moment of inertia about the axis point, the point where the pendulum is swinging from. R is the distance from that axis point to the center of mass of the system. So just make sure you're clear on those. Otherwise, it's a little weird, gets a little complicated, but if you remember it, you're going to get good at figuring out the parallel axis theorem. Okay, so as promised, I'll go back through the homework 13. We have 8 questions. Calculate the hydrostatic difference in blood pressure between the brain and the foot of a person who is 1.6 meters tall, and the density of blood is 1.06 times 10 to the third, which I'm going to write as 1060. So if my density is 1060 kilograms per meter cubed. And my height change is 1.6 meters. 1.6 meters. So I need to calculate the difference as I go up from your feet to your head, right? Brain to your foot. So what is P here and what is P here? Actually, I want the difference. So remembering Bernoulli's equation, if you want, with only the hydrostatic terms, the gravity and the static pressure, assuming there's no V there. We want the change, so P2 minus P1, move that over, is density times G times H1 minus H2. And if we assume H1 is 0, then H2 is 1.6. So P2 minus P1 is rho G H2 with a minus sign. This is 1060. This is 9.8. This is 1.6. There is a negative sign. The pressure change is a drop as you go from your feet to your head, which we already know. And I get 16,620. I don't know, this is in pascals, what they want the answer in. So 16,620 is in pascals. So all we had to do was use Bernoulli's equation here. We left off the velocity terms because we don't need them in the pressure change. Know that they want the change in pressure. So they want P2 minus P1 or P1 minus P2, whichever way. It'll give you the same answer. And then choosing H to be 0 on one side. If this is 1, then this is H1, and this is H2. This is 1.6 meters. Making sure that you get the sign right. Although they didn't want a negative sign. Okay, so for 2, we have a snorkeling elephant and a snorkeling human. They want the difference in air pressure against the body for a 30 centimeter snorkel. So you're assuming that 30 centimeters and 4.5 meters. I guess it's just for humans. So we want the pressure difference, air and water pressure, 30 and 4.5. Okay. So this question relies on the fact that you have to know that the pressure up here is 1 atm, which is 1.01 times 10 to the 5th pascals. And the pressure down here was 30 centimeters or 45 meters. So we're going to go 30 centimeters or 4.5 meters. In the first case, pressure initial, pressure final. So let's write it as pressure initial plus rho GH initial is equal to pressure final plus rho GH final. Note, however, this will be air, this will be water. We're going to say that our H final is whatever our H's are, and our H initial is 0, so this will go away. And they wanted to know in atmospheres what the difference is. So they want P final minus P initial, which is delta P, which in this case is, delta P is rho of the water GH final with a negative sign. So if I move this over, what I get is P final minus P initial is negative rho GH final. But these will be negative for H final. So the negative sign will go away and we'll just treat these as normal numbers. Okay, density of water is 1,000 kilograms per meter cubed, gravity 9.8, H final is 0.3. What does that change? They wanted in atmospheres. I'll show you how to do that in a second, but times 9.8 times 0.3 is 2940 pascals. And when it's 4.5, 1000 times 9.8 times 4.5 is 44 100 pascals. So 1 atmosphere is 101,000 pascals, let's say. So 2940, or there's 1,000 per atmosphere. So if we divide our pascals, our number in pascals by that, we'll get atmospheres. 2940 divided by 101,000 is about 0.03. This is about 0.03 atmospheres. 44,100 divided by 101,000 is 44-ish, so 0.44-ish. I got 0.029, so 0.03, and I got 0.44. Let's see what they're using for their numbers. They're using 998 kilograms per meter cubed for the density of water, and they're using 9.8. They are using 1.01 times 10 to the 5th pascals for an atmosphere. So 3 sig figs. Alrighty. 3 is Pascal's principle. So here we have, let me go get my dog for a second. Sorry, I think my old dogs are senile. She'll forget why she's outside. Oh, yes. Okay, so Pascal's principle says AF, little a, f is equal to big A, big F. So if the piston diameters are given, what magnitude will produce the big force? So 2.78 and 46. So diameter 1, 8 centimeters, and diameter 2 is 46 centimeters. For me, little f and big F. Big F we want to be 26.2 kilonewtons, which is 26,200 newtons. Now, our area, little a, little f is equal to big, nope. We're doing pascals. Pressure. Pressure on one side is equal to pressure on the other. Big F, big A. Now, each of these we're assuming is round, so little a is pi times d1 to the half squared in meters. Big A is pi times d2 to the half squared. Radius of a circle is pi r squared. Half the diameter is r. So this would end up being, put it in meters, 0.0278 meters divided by 2, square that answer, times pi, and I get 6.07 times 10 to the negative 4 meters squared. 46 turned to centimeters is 0.46 divided by 2, multiply that answer by itself, and multiply by pi, and I get 0.1662 meters squared. Very small. Now we want to find F. So F is simply A over big A times big F. You could do this a couple ways. Now that you have these, you could just stick them in. Or what you could do is you could put them in this way. So pi d1 to the half squared over pi d2 to the half squared times F. That would mean that the pi's and the 2's would all cancel, and you would get d1 squared over d2 squared times F, which works too. So 2.78 divided by 46 times itself times F is 26,200. is 95.7 newtons. 95.7 newtons, okay? Big takeaway here though, Pascal's principle says the pressure is equal where it goes in and where it leaves. That means F over little a is big F over big A. From there, it's pretty easy to solve as long as you remember that these are circular pistons, so they have an area of pi r squared, and that r is half the diameter. Okay, block of wood floats in fresh water with 8.846 submerged, and in oil 0.89. So we want the wood and the density. Fresh water 0.846, and in oil 0.849. Did I get that right? 891. Submerged. V. Okay, and they want us to find the density of the wood. So buoyancy, remember, if it's floating, there's no acceleration, but there's a force of buoyancy up minus the weight of the object down. The weight of the object is the object's density times the volume of the object. Okay, so let's do this top one here. And the force of buoyancy is the mass of the water times G, the water displaced, which is equal to the density of water times the volume of water, which is equal to the volume of the volume displaced, I should say, times G. So we have density of water, volume displaced times G is equal to the density of the object, the volume of the object times G. The G cancel, what we get is density of water, volume displaced is equal to density of object, volume of object. So the density of the object is density of water, VD over V of the object. VD, we said, was 0.846 in fresh water. V naught over V naught, and water, if we use their 998 or whatever, 998 for the density of water, I get that the object's density, or the wood, should be 0.998, sorry, not 0.998, 998 times 0.846. The volumes canceled. That's how you have to write this so that you can cancel the volumes. This is the volume displaced or the volume submerged. So 998 times 0.846 gives me 844 for the density of the wood. See if I'm right. They got 846. Why did they get 846 when I got 844? Because they used 1,000 this time. I do not understand why Wiley does this, and it's one of the many things that angers me with Wiley. They changed the density from the last problem where they used 998 to 1,000 here. Okay, fine. So the density of the wood is therefore 846. Because this is 1,000. All right. So if the density of the wood is 846, now in the oil, it's going to float the density, or yeah, the density of the oil, the volume displaced times G has to equal the density of the object, I should put oil, which in this case is the wood, times the volume of the object times G. And VD, we said, was 891 times volume of the object. That's how much of it displaced or submerged. So the density of the oil is density of the water, volume of the object G divided by volume displaced G. These go away. VD is, so this is density of water times volume of the object, 0.891 volume of the object. These go away. And so the density of the oil is density of the wood 846 divided by 891. And that gives me 846 divided by 0.891, 950-ish, 950 kilogram meters cubed. Yep. Okay, so the idea here is that for buoyancy, when an object is floating, A is 0, but it's equal to FB minus mg. Density is mass over volume. So mass is density times volume. And the volume of water displaced times the density of water times G is the force of buoyancy. So you get 0 is density of water, volume displaced, G minus density of object times volume of object times G. And if you write the volume displaced in terms of volume of the object, you can cancel that. And then you're just only dealing with the density of water and the density of the object. Not too bad. Question 5, what fraction of an iceberg would be visible if the iceberg floats in the ocean in a river? Okay, so we have, again, I don't know why I keep doing that. We have a buoyancy issue here. And what we want to know is the volume displaced. So the density of the water times the volume displaced in the water, G, is equal to the density of the object, the volume of the object, times G. G cancel. So the volume displaced is density of the object, volume of the object over the density of the water. And they want to know how much they want to know what fraction would be visible. This is going to give you a fraction. So 1 minus this is actually the fraction you want because you want what's visible. Here, the density times or divided by saltwater 1024, 998. 1024 for salt, 998 for fresh. The iceberg is what, 917? Yeah. All right, so this would be for the first one when it's in salt water, that would be 917 over 1024 or 0.8955, 8955 of V naught, 89%. So if I subtract 1 minus this answer, the portion above would be 0.1045 or 10.45%. Here, when it's fresh water, this would be 1 minus 917 over fresh water, 998. So 1 minus 917 over 998 is 0.0811, maybe 0.812 percent. So 8.12%. So 1045.0812. Not too hard. Garden hose with an internal diameter and connected to a stationary lawn sprinkler, which has 26 holes each with 30 centimeter diameter. 0.30, I should say. If the water in the hose has a speed of 0.91, at what speed does it leave the sprinkler holes? So this is a Bernoulli's equation. We have P1 plus rho GH1 plus rho V1 squared over 2 is equal to P2 plus rho GH2 plus rho V2 squared over 2. V1 times A1 is equal to V2 A2. There's no change of height. But the areas, so area 1 has a diameter of 34 centimeters. And area 2 has 26 holes, each with a diameter of 0.30 centimeters. So there are 26 of those. We'll come back to that in a minute. There's no height change. And when they leave, oh, we don't need to know that at all. We only need to use this. We just want V2. So V2 is V1 times A1 over A2. But if we assume that they're round, then, is it not? Oh yeah, it is 0.30, huh? Let's put these into meters. A1 would be 0.34 meters. A2 would be 0.003 meters. But that's the diameter. So the area is pi radius squared, which is equal to pi d to the half squared. So again, we get V1 pi d1 squared over 2 over pi d2 squared over 2. The pi's and the 2 squareds cancel, and you get that V2 is V1 d1 over d2 squared. And those you don't really need to convert. So 34 divided by 0.3, but there's 26 of these. So it's not 34 divided by 0.3. It's 34 divided by 26 times 0.3. Square that, it's 19. So 19 times the velocity at 1. The velocity at 1 was 0.91, so 0.91 times 19 is 17. What did I forget? I just did something weird. Oh, I'm totally dumb. It's 3.4 times 3.4 divided by 0.3 times 0.3, but then you need to divide by the number of holes. And then multiply that by 0.91. Yeah, I just was dumb on my here. Right? Yeah, it's just down here.
Oh, okay. I was wondering.
So the area 2, if there's 26 of these little holes, right, is 26 times pi d squared over 2. And area 1 was just the area of the hose, which was pi d, d1 squared. Okay, so that, if you cancel stuff, ends up being d1 squared over 26 times d2 squared. And if you use v2 is a1 over a2 times v1, so v2 is times v1. And you'll end up with like 4.5-ish meters per second. All right, so that one's just watch your algebra. Here, water is moving through a pipe with a cross-sectional area of 44 centimeters squared. The water gradually descends 10 meters and the pipe increases to 8. I want the speeds. So again, is there another one after this? If we run out of time, these two, this one, the pressure difference is P2 minus P1. And then the volume flow rate is AB of either one. The area times the velocity of either part. The mass flow rate is simply AB times the density of water. Let's try and do this one real fast. Because this is a Bernoulli's problem, which means all you're going to do is you're going to write P1 rho G H1 rho V1 squared over 2 is P2 plus rho GH2 plus rho V2 squared. And we have A1 V1 is A2 V2. Now, we're going to try and find P1, H1 V1, maybe A1, and P2, H2, V2, A2. So we're told that V1 is 66.3 meters per second. We're told that the cross-sectional area there is 4.4 centimeters squared. You don't have to change these areas because if you're dividing them, they cancel. But you may need to if you're not dividing them. The water descends, meaning negative. It decreases in height to 10 meters, and the pipe increases to 8 centimeters squared. So A2 is 8 centimeters squared, but H2 is minus 10 and H1 is 0, or H1 is 10 and H2 is 0. It doesn't matter which one you do. So what is the speed at the lower level? If the upper pressure is 1.4 times 10 to the fifth, what is the pressure at the lower? So 1.4 times 10 to the fifth pascals. Now, first of all, they just want V2, right? What is the speed at the lower level? That we only have to use this for. So V2 is A1 over A2 times V1, which would be 4.4 divided by 8 times 6.3. That is 4.4 times 6.3 divided by 8, 3.465. 65 meters per second. So 3.465 meters per second. And then we want the pressure at the lower level. So looking at this, we want P2 is equal to P1 plus rho G H1 minus H2 plus rho V1 squared minus V2 squared over 2. And now it's just a matter of plugging in numbers, assuming rho is 1,000 kilograms. So P1 was 140,000 pascals plus 1,000 times 9.8. H1 minus H2 is times 10. And then plus 1,000 divided by 2 is 500 times V1 squared, so 6.3 times 6.3, minus V2 squared, 3.465 times 3.465. And I get 251,841 pascals, assuming I did this right, which I may not have. 251,841, exactly what they got. So this one is the exact same deal. It's just that, remember when you write Bernoulli's equation, because you have P1 rho G H1, rho V1 squared over 2 is equal to P2 plus rho G H2 plus rho V2 squared over 2. You can set this as the change in pressure, which would then be equal to rho G H1 minus H2 plus rho over 2 V1 squared minus V2 squared. And don't forget you have A1 V1 is A2 V2. So they tell us that the density of the liquid is only 900 this time. They give us the cross-sectional area of each one. They want the pressure difference, they give us the pressure difference. So we want A1 V1 or we want A2 V2. They told us A1 and A2. They told us delta P, A1, A2, and they told us density. So we need to find V1 or V2. Well, we can actually put this in as V1 because V2 is equal to A1 over A2 V1. So we can substitute that in here. And what we get is times A1 over A2 squared times B1 squared. So you can then solve this because you were given delta P. You can assume that the horizontal pipe has no change in height. So this term goes away. And so this is just delta P is this. Solve this for V1, 900 over 2, which is 450. So I would get delta P over rho to the half, 1 over 1 minus A1 over A2 squared is equal to V1 squared. All I did was rearrange that stuff. So delta P over density to the half, delta P is 7.8 times 3, divided by half of that is 450, and then divided by 1 minus, what was this, A1, A2, so 2.4 to the minus 2, so 0.024 divided by 0.093 times 0.024 divided by 0.093. And I get 1, take the square root of that answer, 1.035. Why am I off by 10? Oh, I forgot my G. Divide also by G. I forgot to divide. No, I didn't. Why am I off by? I'm off by a 10th for some weird reason. I don't know. I probably did something in my calculator, and I don't want to go back and find it right now. But essentially, once you find this, you get your V1, and once you have V1, you can just do this. That is your volume flow rate. If you multiply it by the density, that is your mass flow rate. So mass flow. Because, yeah, that's essentially the volume there. So, really don't know why I'm delta P. They did do a bunch of stuff. I don't know why I'm getting a 10th. Unless, did I? So the initial pressure is 7,800, right? 7.8 times 10 to the third. 7,800. Divided by half the density, which is 450. And then that has to be divided by A1 over A2 is 0.024 divided by 0.093. Times that answer. And 1 minus that answer. And then 1 over that answer. Something. Oh. All right. And then times it's so weird. Yeah, I don't know. Something's weird with that answer. But regardless, we're done anyway. So if you want to pause it and look at that, the way they did that, they essentially solved it like that. Yeah. I don't know. I'm doing something weird. I should be getting the same answer, but I'm not. Oh, because they want the volume flow rate. That's why. I'm just being stupid. Anyway, yeah, good luck. If you need help, call me or text me. I'll see you guys in a couple days.